Good morning, good afternoon, ladies and gentlemen. Welcome to another series of online lessons. If you haven't already, please subscribe to the channel and leave a like for this video. So please remember to subscribe so that the channel grows. Now, in today's lesson, we are in advanced integration, and basically we are going to prove the constant rules for the Riemann sums and the constant rules for the double integrals. All right, so starting with the left side of the equation, and for some D, which is the region that we've been given here, which we can define to start from A and end at A2 in the X, and start at B and end at B2 in the Y, and where N and P are subregions of D, the summation of this function, or the double summation of this function over D, can be written as the sum from 0 to n times the sum from 0 to p of the function of the product. So we can redefine the sum like that, and by definition, the limit as n comma p approaches infinity of this function from 0 to n, from 0 to p of c of x comma y dx dy, this becomes the full sum, which is the integral from a1 to a, well, let me start with the y part so that it becomes dy dx dy. So this is b1 b2 a1 a2 c of x comma y dx dy. So this basically by definition of Riemann sums, the limit as n comma p approaches infinity of the integral of that. Then what we're going to do here, we're going to use the constant rule of integration. So by the constant rule of integration, which says the double integral over any region D of c of x comma y dy dx could be in any order is equals to c over the double integral of c of the function x comma y dy dx. So using this property, we can rewrite this as limit as n comma p approaches infinity of sigma from 0 to n, sigma from 0 to p of c of x comma y dx dy equal to, so here we can factor out the c, so this will become c b1 b2 a1 a2 f of x comma y dx dy. Okay, so now here we'll say, but the integral from b1 to b2 a1, a2 of f of x comma y dx dy. This is equal to the limit as n comma p approaches infinity of the sum from 0 to n, from 0 to p of the function. There is no c, so of the function x comma y dx dy. Let me see, dx dy, like that. So basically what we can do is we can now replace here with this. So what we're going to have is limit as n comma p approaches infinity of sigma from 0 to n, from 0 to p of c of x comma y, change in x, change in y, will be equal to the c outside here. Then remember this part is that part. So then we say limit as n comma p approaches infinity of the sigma from 0 to n, and from 0 to p of f of x comma y dx dy. Okay, so basically that's the idea. And we can say hypothetically the limits can be removed because they are the same. So what we're going to remain with is summation from 0 to n, summation from I equals to 0 to p of c of x comma y, change in x, change in y will be equal to this c that is here, c, then summation from 0 to n, summation from 0 to p of f of x comma y, then dx dy. So basically this is the proof, and we know this can be written as the sum over the region D of c of x comma y, change in x, change in y, which is on this side, c, change in x, I mean the double sum over D of f of x comma y, change in x, change in y. And therefore, that proves the first property, or the first constant property of the Riemann sums. So basically, that's a run through. So here, what we did here is that these, if their limits are equal, then we can just simply say their functions are also equal, so we can get rid of the limits there. So this is the first one. So now we go on to proving the constant rule for integrals. All right, so now we do the second part. So this is prove the constant rule for this integral. So again, we're going to start with the left hand side. So again, we're going to define D as a region that starts from A1 to A2 in the X direction, and B1 to B2 in the Y direction. Sorry, let me see. B1 to B2 in the Y direction. Primary. B2. b2 in the y direction, like that. So now the integral over d of c of x comma y can be written as the double integral from a1, let me see, dx dy. So this is the dx dy, can be written as the integral from a1, let's say, okay, we put the b's outside. So we say the double integral from b1 to b2, a1 to a2 of c of f of x comma y dx dy. Okay, so just to keep constant with x part, the a's, and the y's part for the y's. Now here we're going to consider the distributive property of a constant. So by the distributive property of a constant, when you have a constant outside of a function, we can simply take the function, or we can simply take the constant inside the function. So this becomes f of c times x comma c times y. So that is the distributive property of a constant. So x comma y, we can distribute the constant inside. So our double integral over d of c of x comma y dx dy. So I've simply rewritten this. So this will basically just be equal to the integral from b1, b2, a1, a2. Then we can take the constant inside. So c of x comma cy dx dy. Okay, then here we're going to use the fundamental principle of integration. So basically this will start by integrating first. So what we'll say is we're going to let c of x comma c of y be equal to the integral of this function c of x comma c of y dx. So we'll put x there to show that it is coming from the change of x. So now if we let this be the integral of the inside part here, by the fundamental theorem of integration, the integral over d of c of x comma y dx dy will be equal to, so we write this, so this will be the integral from b1 to b2. Then basically when we integrate this, what it will become, it will be capital F with respect to x of cx comma cy. Then we are going to put in the limits. Let me just write this properly. Cx comma cy, and we're putting in the limits a1, a2, dy. So basically when we put in the limits, this becomes equal to the integral from b1 to b2 of we start with the upper limit. So f with respect to x, then we're only putting in on x part. So this would be c times a2 comma c y minus fx c a1 comma cy um, dy. So this is basically the theorem. So here we see that by the distributive property, again, we can factor out the constant. So this can be written as integral from b1 to b2. We factor out the constant c. C is here. So what we're going to have is fx a2 comma y minus fx a1 comma y, like that, dy. Okay, so now we're here. So now here we're going to let some function, we'll say g of a. We see that their a is on y, so we just put general a comma y be equal to this function here. So just to simplify our x, so g a2 comma y minus fx a1 comma y. Then what we're going to have for our integral over d of c of x comma y dx dy is, we're going to have this double integral, single integral from b1 to b2, the constant which is outside here. Then what we're going to have inside here is g of a comma y, then dy here. Okay, so that is what we're going to have. So now again, we can distribute the constant inside. So again, you say let c of g a comma y equal to g of c of a comma c of y using the distributive property. What we're going to have is the integral over d of c of x comma y dx dy will be equal to the integral from b1 to b2. We distribute inside, we're going to have g of c times a comma c times y dy. Okay, again we're going to let let me put a different color for letting. So we're going to let capital G, which we have a constant on the x times a comma a constant on the y times y, be equal to the integral of g of c a comma cy dy. Okay, so if we do that, then our integral over d of c of x comma y dx dy will basically be equal to, so this will change to g, capital G, of constants of a, c, y. Then we're putting in the limits from b1 to b2. And basically, when we plug in the limits, this becomes g of c a. So we are plugging in the limits on the y because we were differentiating with respect, we were integrating with respect to y. So this becomes ca comma c c, this will be b2 minus g of ca comma c v1 And here we see that there is C, 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 C. So we can simply factor out C. So C can be factored out. And what will remain with is G of A comma B2 minus G of A comma B1. Okay. Then using the fundamental theorem of calculus, so by the fundamental theorem, the integral over d of c of x comma y, the x dy will be equal to, so there is a c outside here. So this now can be written as the integral from b1 to b2. So basically we're just reversing. So we had reversed. So we're just reversing. So on the y, so the b goes there. Then we have g of small letter g. So this is g of a comma y, then dy. So when we integrate this, this is where we're going to have capital G. So this is where we're going to have that. So now from here, you say, but what is g of a comma y equal to? Well, when we look what we did here, g, what is that? G of a comma y is equals to this, which is right here. So we're going to have this. So we see that g, we made g equal to this, so we can replace this with that. So basically, what we're going to have is the double integral over d of c of x comma y. The x dy will be equal to, so we have a c outside here, then integral from b1, b2. Then we have this becomes this, so f x a2 comma y minus f x a1 comma y. Then we have a dy here. So again, using the fundamental theorem of calculus, let me just put it right here. So using the fundamental theorem of calculus, so by the fundamental theorem, the integral over d of c of x comma y, the x dy will be equal to the c outside here, b1, b2. So we see that there is a here and there is a1 there. So this becomes a2 over here, a1 there, and this becomes small letter. Then this basically becomes x comma y. Then we're looking at the x. So actually this is dy, sorry for that. So this is dy from here. So this is dy from here. I don't know why I wrote x, so apologies for that. So this is dy, and here simply we were replacing out from the x part, so this becomes the x for a and dy for the b's here. So it's supposed to be like that. So we see now that this can also be written as c, then the integral over d of x comma y dx dy, and that proves the theorem. So basically, to run you through what we were doing, so we started from here. We started with the left hand side. We said we let D be the region that stretches from A1 to A2 in the X and B1 to B2 in the Y. And basically we got the integral. We can rewrite it in an iterated form, which is this form that is right here. Then by the distributive property of a constant, we know that when a constant that is common everywhere can be factored out and it can be distributed back inside. So which we did here. Then from here, we said this integral can now be written as this, where we distributed the constant inside. And using the fundamental theorem of calculus, we can start with integrating the inside here, or using Fubini's theorem, so we can calculate what is inside here. Then if we let the integral of what is inside here be equal to this, then by the fundamental theorem of calculus, we can replace in the variables, the limits. So the upper limit, and we were integrating with respect to y, so we replace on the y parts. So the upper limit on the y part will be CA2 and CA1 dy. Then we simplify. Again, C is everywhere. We can factor out C. We can factor out C. Then we let this be a function that will have A's and Y's, because A here can be different terms. So we just generalize the A and the Y like that. Then what we're going to have is the integral over D of that will be equals to C, then G A Y dy. And again, by the distributive property, we can put the C inside here so that we have C of A, Cy, dy dx like this. Then if we let this be the integral of this, which is this here, then what we're going to have is the integral over D equal to G of this, which is the integral of this. Then we replace in the limits. So we're doing with respect to y, so the limits will be replaced on y, which is here where we replaced, like this. Then here we can factor out the constant C like that. Then here, by the fundamental theorem of calculus, we just start reversing. So this now, okay, for this, okay, we start reversing. So by the fundamental theorem of calculus, so this can be written as, or D becomes C, then the upper limit B2, the lower limit B1, then the function or the anti-derivative anti-integral or antiderivative of that, so which is that. Then this can be, we remember that this was equal to that, so we just replace in back again using fundamental theorem of calculus. This becomes that, like that. So basically that is what we're going to do for today. Then in the next lesson we'll see what we can catch on.